Hello, this is the fourth video in my series Statistics for Sustainable Development. Today we are looking at the topic of correlation, a measure of the relationship between two variables. In this video we will find out how to calculate the variance, the covariance and the correlation coefficient. Recall from previous videos that I've been using data from the Young Lives study conducted by the University of Oxford. We've been using a sample of 1,906 babies aged between 6 months and 17 months who were living in Ethiopia in 2002. Each of these babies had their height measured, and this was compared to the World Health Organization growth standards to see whether they were big or small for their age, relative to a healthy growth trajectory. In video 1, we looked at how a Z-score was calculated for each child, where positive scores indicated the child was taller than the median healthy child, and negative scores indicated that the child was shorter than the median healthy child. In video 3, we saw that the mean or average Z-score for our sample was minus 1.07. I also introduced you to two children from the sample. These are both real kids, but we've given them made-up names. Mohammed is our boy from Addis Ababa, who has a height for age Z-score of minus 0.95. And Mariam is our girl from Amhara, who has a height for age Z-score of minus 2.13. Now, the survey that was conducted in Ethiopia didn't just measure children's heights. A lot of other data were collected about these children and their families. This included information about the family's housing quality, including size and construction of dwelling, access to services, including access to electricity, water and sanitation, and number of consumer durables owned by the household. These different factors were combined to produce a wealth index for each child. We don't need to worry too much about how it's calculated, except to say that households with a low wealth index score less well on these measures and households with a high wealth index score better on these measures. The wealth index is on a scale of 0 to 1. This means that children from the poorest households have a wealth index close to 0, and children from the richest households have a wealth index close to 1. The sample mean of this variable is found to be 0.17, suggesting that the children in our dataset are quite poor on average. This wealth index has relevance to a number of sustainable development goals, including SDG 1, which targets reduced poverty and improved access to land and basic services, SDG 6, which aims to improve access to safely managed drinking water, sanitation and hand washing facilities, and SDG 11, which targets inadequate housing. So where do we find Mohammed and Mariam on our wealth index? We see that Mohammed has a wealth index of 0.41, which means his family is relatively wealthy. Mariam's family, on the other hand, is much poorer, as she has a wealth index of just 0.01. The rest of this video is going to involve a bit of maths and some algebraic notation, but don't worry, as our clever owl will take us through it step by step. First, let x equal the wealth index of the household, and let y equal the height for age Z-score of the child. Now, I know it might sound a bit odd to use the letter y to denote a Z-score, or x to denote wealth, but we're just using these letters as this is conventional notation when we have two variables that may be related to each other. If you put a bar over the x and the y, this denotes the sample mean of that variable. Remember that the mean is calculated by adding up all the x's or y's respectively and dividing by the number of children in the sample, denoted as n. What you see here is just the mathematical formula for the mean, where the sigma tells us to find the sum or the total. We've already worked these out from our data. The sample mean of the wealth index is 0.17, and the sample mean of the height for age Z-score is minus 1.07. The next thing we're going to do is calculate how far away each of our children are from the sample mean by subtracting the sample mean from each child's individual value. First, Mohammed. As we've seen, he has a wealth index of 0.41. This is 0.24 above the sample mean of 0.17. Mohammed's Z-score, the y variable, remember, is also above the mean, minus 0.95, compared to minus 1.07, so a difference of 0.12. Mariam, on the other hand, has a below average wealth index, which is represented by a negative difference equal to 0.01 minus 0.17, which is minus 0.16. She also has a below average height for age, so again we end up with a negative difference, this time equal to minus 1.06. We can use these differences to calculate the variance of x and y respectively. The variance, or specifically the sample variance, is the sum of the square of all these differences divided by the sample size n minus 1. Mohammed has a wealth index of 0.24 above the mean, so we find the square of 0.24. Meanwhile, Mariam has a wealth index of 0.16 below the mean, so we need to find the square of minus 0.16. We do this same calculation for all 1,906 children in our sample, working out how far away they are from the sample mean and then squaring that difference. Notice that whether the difference is positive like Mohammed or negative like Mariam, the squared difference will always be a positive number. We add all these squared differences together and then finally divide by the sample size 1906 minus 1, which is 1905. Of course, I haven't done this calculation by hand, but with help of a computer, this gives us a variance of 0.03. As both the top and bottom of this fraction will always be positive, the variance will therefore always be a positive number. If most of our individual values are quite close to the sample mean, the sum of squared differences will be quite small, and the variance will be small. If you have a lot of children who are a long way from the sample mean in either direction, then this, of course, will increase the sum of squared differences and lead to a larger variance. So, we get a small variance when the data are clustered around the mean, and a large variance when the data are more spread out. Hence, the variance is a measure of how spread out or dispersed the data are on that particular variable. Now, this might ring a bell for anyone who's been watching my previous videos. Didn't I say in video 1 that the standard deviation was a measure of dispersion? Yes, I did. So that must mean that the variance and the standard deviation are somehow related. Well, indeed they are. In fact, the standard deviation is simply the square root of the variance, which in the case of the wealth index is 0.17. So we have come full circle. We've already introduced the standard deviation intuitively. Now we have shown how to calculate it from our data. So we follow exactly the same steps for our y variable, height for age, z-score. We calculate the difference between each child's z-score and the sample mean z-score. Square these differences and add them all up, again dividing by n-1, which is 1905. This gives us a variance of 3.56 and a standard deviation of the square root of 3.56, which is 1.89. Recall from video 1 that when expressed in z-scores, the standard deviation of height for age among healthy children is exactly 1. But our sample has a standard deviation quite a bit bigger than 1. And when you think about it, this makes perfect sense. Among our Ethiopian children, we have some healthy children and some malnourished children. So their heights are likely to be more varied than a more homogeneous group of healthy children that was used to derive the WHO growth standards. So we've calculated the sample variances and standard deviations of the wealth index, our x variable, and height for age, our y variable, separately. But what can we say about how these things are related? This is where covariance comes in. To calculate the sample covariance, we still need to find the difference between each x and the sample mean of x, and each y and the sample mean of y. But instead of multiplying each difference by itself, in other words, squaring it, we multiply these differences by each other. So for each child in the sample, we multiply x minus x bar by y minus y bar. For Mohammed, this is 0.24 times 0.12, and for Mariam, this is minus 0.16 times minus 1.06. Again, we add up all these products together and divide by n minus 1. As Mohammed has both above average wealth and above average height for age, the product of these differences will always be positive, as a positive number multiplied by a positive number is always positive. Similarly, as Mariam has below average wealth and below average height for age, her product is also positive, because a negative number times a negative number will always be positive. But there will be some children who have above average wealth and below average height for age, or below average wealth and above average height for age. For these children, we'll be multiplying a positive number with a negative number, which comes out negative. So unlike the variance where we're adding together a series of positive numbers, the covariance involves adding together a mixture of positive and negative numbers. This means that the result could come out positive or negative. In this case, we get a positive result of 0.05. This means that Mohammed and Mariam are typical of the overall sample in that taller children tend to come from wealthier households and shorter children tend to come from poorer households. We can now find the correlation between our two variables, x, wealth of household, and y, child's height for age. By dividing the covariance by the product of the two standard deviations, we can derive the correlation coefficient, which is often denoted by the letter r. This is always a number between -1 and 1. A correlation coefficient close to 1 means the two variables are strongly positively correlated, meaning that high values of x tend to be accompanied by high values of y. A correlation coefficient close to -1 means the two variables are strongly negatively correlated, such that high values of x are accompanied by low values of y. In our case, the correlation coefficient between wealth and height for age is positive, but quite close to 0. So the two variables are positively correlated, but quite weakly so. We can show this correlation graphically on a scatter plot. Here we put the wealth index on the horizontal axis, or the x-axis, and the height for age z-score on the vertical, or y-axis. Each of these blue dots is one of the children in our sample, plotted according to their values on these two variables. These dots are spread out all over the page, so at first glance it doesn't look like there's any relationship or correlation between wealth and height. But when we add a line of best fit to the scatter plot, we can see that the line is slightly upward sloping. This confirms that there is a weak but positive correlation between a family's wealth and the height of their children. We'll be coming back to the line of best fit in the next video. Let's bring our owl back in for a final time and summarize what we've learnt today. We have seen that the variance is always a positive number and is a measure of how dispersed or spread out our data points are on a particular variable. The standard deviation is the square root of the variance, and so is also a measure of dispersion. The covariance from which we derive the correlation coefficient can be positive or negative and tells us the direction and strength of relationship between two variables. You might have heard the phrase, correlation does not imply causality, and this is an important point on which to end this video. Just because wealth and height are correlated, it does not mean that one of these things causes the other. We cannot say necessarily that acquiring more wealth will make your kids healthier, nor can we say that having tall kids makes you wealthy. All we can say from this result is that, for whatever reason, wealthier households tend to have bigger children. We'll be exploring this further in future videos when we look at the tools of regression. But for now, thanks again for watching. Sorry it's been a slightly longer video this time with a bit more technical content, but thanks for staying for the end, and I hope you have found it useful.